talk are or from the preprint available in the archive. Okay. Now, my intention is really to advertise this project, and I think it overlaps in many interesting and different ways with, let's say, toric topology, and not only toric topology. And these are familiar objects, but still I would like to remind you. So what are simple games? Simple games were originally introduced in this famous monograph by von Neumann and Morgenstern in 1944, and then studied by Shapley, Taylor, and Zwicker, and others. So simple games, they are, in a nutshell, they model the distribution of power among coalition of players. Formally, the definition is the first line here. A simple game is just a family of subsets of certain set P, which has the property that the whole set P is, well, this is a family of coalitions, and W comes from winning coalitions. So we say that the whole set is a winning coalition, empty set is never a winning coalition, and if B is a winning coalition, and then any superset is also a winning coalition. So this is very naive at the first sight model for, let's say, voting situation. If you have a parliament, and then some players, representatives of some cities, let's say, they decide to make a proposal, and then they make a coalition and they vote. And it is a question, is it according to some evaluation, is this coalition winning or losing? Now, a simplistic complex is something very similar, very object familiar in combinatorics and topology, very similar in the sense it is dual. And the last sentence here, which says that simple game is simply complement of a simplistic complex, may appear somewhat disappointing. But this is a very interesting situation where essentially the same object, simple game as opposed to simplistic complex, can be studied from two radically different points of view and still interact in a very interesting way. Okay. There are I will mention 2 or 3 or 4 main classes of simple games. First of all, it is weighted majority games. In these games, each player is associated a weight, certain positive number. And there is also a number Q called a quota, a threshold. And then you decide if a subset of players or a coalition is winning or not, depending on what is the total weight of all players from that coalition. And if the total weight is, let's say, greater or equal than the quota, the threshold, then of course the coalition is winning. And in the opposite case, it is losing. So here from the point of view of simplistic complexes, we would talk about threshold simplistic complexes. We say that all subset with total weight less than the quota, they form a simplistic complex, and it is usually called a threshold simplistic complex. So that was weighted majority game. There is something called a roughly weighted simple game. Very similar at the first sight. Again, we have weights or weighted distribution on the players. And again, we have a quota, a threshold. But this time, the definition is somewhat relaxed. If you look at the formulas 1, 2, and 3, it is similar. First 2 formulas are very similar to the previous conditions. If the total weight is strictly greater than the quota, and then it is a winning coalition. If the total weight is strictly smaller than the quota, then it is a losing coalition. But if it is equal to the quota, then you have no information. Maybe they will apply some other special rule which is needed to, what they say, to break the tie, to somehow decide what is it winning or not. And here I will mention one of the central how to call it, central objects related to simple games. It is called trading transform. So trading transform is, well, it is very important thing. So let me very carefully review what it is. So it is a sequence of subsets, x1 up to x sub k, and y1 up to y sub k. And it is a trading transform if all x's are winning coalitions, if all y's are losing coalitions, and if these two sums of characteristic functions are equal. So phi, or sometimes we say k, chi of A is just the characteristic or indicator function of given set A. And let me check my next slide. Okay. This is one example. If you have a simple game where the losing coalitions are essentially sets 1, 2, 2, 3, 3, 4, and 4, 1. So they form a cycle in a 4-element ground set. And then you observe that losing coalitions are 1, 2, 2, 3, 3, 4, 4, 1, while winning coalitions are 1, 3, and 2, 4. And this is obviously a trading transform. If a trading transform exists for a given simple game, it guarantees that it is not a weighted majority game. And it is clear because on the left-hand side, if you integrate in some sense with respect to the weight distribution, on the left-hand side, you will obtain something less than 4 times the quota. And on the right-hand side, you get something greater or equal than 4 times the quota. And of course, it's not possible. So every time you have a trading transform like this one, then you can guarantee that it is not a weighted majority game. Now, what about roughly weighted? Roughly weighted simple game. This time it appears that it cannot be easily tested with trading transforms, but actually quite the opposite. If you have a trading transform like this, and if among the losing coalitions is at least one empty coalition, and among the winning coalition, if there is at least one grand coalition, all players, then you can guarantee that it is not roughly weighted game. Okay. And now, just to be rewarded for listening to these definitions, I want to mention a beautiful game introduced, I think, already by von Neumann and Morgenstern. It says, take the Fano plane, projective plane with finite projective plane with 7 vertices and 7 lines, and you say this is a game with 7 players, vertices, and we say that a coalition, a subset, is winning if and only if it contains a line. So minimal winning coalitions are lines, and complementary sets are losing coalitions. They are, it turns out, precisely the sets which are not winning. And this is it may appear to be very strange because winning coalitions are of smaller size than some of the losing coalitions. So a line is of cardinality 3, and some losing coalitions have cardinality 4. But what is remarkable about this funny game, one of the remarkable things is that there exists a trading, how did I call it? Trading transform. Oops, sorry. I triggered, sorry, stop. By accident, I triggered. Okay, let me check. I will stop sharing for. Oh, no. Okay, I understand what happened. Okay, very good. Please let me know. Can you hear me and see what see the screen again? Anybody, please?
Yes,
Hello.
Yes,
We can see the screen, yes.
you can see the example. Sorry, it was a little accident. Okay, fun again. So there exists trading transform which involves all winning coalitions and which involves one empty coalition. I leave it to find it that trading coalition which proves that this is not a roughly weighted game. And this is another example, simpler. Please look at the pentagon on the right. It is a simplistic complex of losing coalitions, a cycle of losing coalitions. The dual of this simplistic complex, Alexander dual, is the minimal triangulation of the Möbius band. And what we see below is a trading transform, which does not involve a grand coalition. So this just proves that this is not a threshold complex. So this is not a threshold complex. This is an important object, and I wanted to introduce it early enough. Okay, and Bier sphere is another important object, which we study in these papers. Formally, you take a simplistic complex K, take its Alexander dual, which consists, it is simplistic complex which consists of all complements of all non-simplices. Take the deleted join of these two objects, and you obtain, it turns out you obtain a simplistic complex, which is a combinatorial sphere. It is called a Bier sphere after Thomas Bier. And well, I introduced this for those who will read these transparencies later, so I will just continue. Let me check. So Bier sphere is defined as deleted join of the simplistic complex and its Alexander dual. It turns out, well, one of the main questions we want to study is when these spheres are polytopal. In other words, when they can be realized as boundary spheres of simplistic convex polytopes. It turns out, somewhat surprisingly, which was established in our first paper, that each Bier sphere, a combinatorial object, admits a star-shaped embedding in an Euclidean space. It is known that there do exist simplicial spheres which are not star-shaped. It cannot be. So it is known, of course, many of them are not polytopal, but even some of them are not even star-shaped. And it turns out that Bier spheres are star-shaped. And moreover, if you look at the radial fan from the inner point of a Bier sphere, which is star-shapedly embedded, you obtain a complete simplicial fan. And this fan actually turns out to be a coarsening of the braid arrangement fan. And we recall that the braid arrangement fan is the normal fan of the permutahedron. And it follows that Bier sphere, if canonical with this, if polytopal with this fan, it is a generalized permutahedron. It is the formation of a permutahedron. But for now, I just would like to ask you to remember these two objects: Bier K, which is Bier sphere, and the associated fan, complete simplicial fan. This is one example, but since the time will go very quickly, maybe I will briefly explain this picture with maybe this example is important to understand before I proceed. So this is an example where I take a simplistic complex K, on 4 vertices and take the skeleton. So in this picture, imagine that you have a red triangle with 4 vertices, and inside that triangle simplex, a tetrahedron, and in this tetrahedron you take all edges. So this is complete one skeleton, and this is the simplistic complex K. Its Alexander dual K is zero skeleton of this tetrahedron, and we realize it in the dual simplex tetrahedron, which is blue one. And then if you draw all the simplices, then you can see that the Bier sphere in this case is just a triangulation of the boundary of this cube. So cube is the convex hull of the union of these two tetrahedra. And in general, if you have a union of a simplex and its dual simplex, you obtain a convex polytope, which is called by John Conway a diplosimplex. It is a very interesting object which we came across naturally in our study, and it doesn't seem to be so well known in the theory of convex polytopes, but some people, of course, used it, like John Conway, and they established very interesting results about diplosynthesis. But that's another story. And this is something I talked about earlier. For example, I think I talked about this in Petersburg last fall. Here, I will just mention this in passing. So when you have a simplicial complex, you can see it complex of losing coalitions. So that's simplicial complex seen from the point of view of simple games. But you can see it also as an object producing Bier sphere. Bier sphere is now combinatorial geometric object in the topology of simplicial spheres and convex polytopes. But you can also associate to a simplicial complex a polyhedral product or generalized moment angle complex, which has also two additional objects, two spaces X and A. And I will not, again, follow this very much, but I just want to ask you, it is always interesting when you have the same object, simplicial complex, to look at it from many different points of view, simple games, polyhedral products, Bier spheres, and to try to recast the definition using different languages. For example, here I express the definition of here and here, the definition of polyhedral product in terms of winning coalitions, for example. But I will pass. This is just for those who look at these transparencies, to look at these connections and maybe find some some questions interesting to work on. Okay. So in general, the problem of deciding if a given triangulation of a sphere is realizable as the boundary of sphere of a simplicial convex polytope is well known. It is the so-called simplicial Steinitz problem. And from this point of view, it is known by a non-constructive argument, a very non-constructive argument, that the vast majority of Bier spheres cannot be realized as boundaries of convex polytopes. They are non-polytopal. Okay, here it is the time to tell you about some new results from the preprint number 3 I mentioned. So this is, you can look at the conclusion, which says weighted majority games correspond exactly to canonically polytopal Bier spheres. So we see we have simple games and Bier spheres, and now we see that one property of simple games is precisely matched with another property of Bier spheres. What is the property? It says, we already know what is weighted majority game. That's the first class I introduced. And And here it says that K is a simplistic complex of losing coalitions of a simple game, of a weighted majority game, if and only if the fan I introduced is polytopal, and it implies polytopality of the Bier sphere. And this kind of polytopality, which is very strong, with very special normal fan, we call canonically polytopal. It is polytopal in the best possible way. So K is a threshold complex if and only if Bier sphere is canonically polytopal. That's the first theorem. The second one characterizes roughly weighted simple games. So we remember that the conditions in roughly weighted simple games was much more general, much larger class of games are covered by this concept. And here it turns out by theorem 2 that the coalition of weighted simple games, of roughly weighted games, is characterized by the property of the fan that it is pseudo-polytopal, that it refines the normal fan of a convex polytope. So roughly weighted games are also precisely matched with the corresponding concept of Bier spheres. And now a little bit of experimental mathematics and algorithmic mathematics. So Bier spheres are simplistic spheres on certain number of vertices. If you have a simplistic complex K on n vertices or n players, then Bier spheres has dimension n minus 2. And now this is an old problem. For example, by Frank Lutz in his paper, well-known paper about classification, about listing of simplicial spheres with certain number of vertices, says that there is this number, several 100,000 combinatorial spheres with 10 vertices. And the problem of deciding which of these spheres are polytopal and which are non-polytopal is, as far as I know, still wide open. We should recall that if we have 7 vertices, all simplicial spheres with 7 or less vertices are polytopal. There are precisely 2 spheres with 8 vertices which are not polytopal. It is Brickner or Grimbaum-Sridharan sphere and Barnett sphere. And now, when we look at spheres with 9 vertices, it was a major project which took maybe several decades to classify which of them are polytopal and which are not. And it is by contribution of Altschuler, Steinberg, and completed by Altschuler, Bukowski, and Steinberg. But with 10 vertices, it is still open, and let alone with more than 10 vertices. So I ask here, what about Bier spheres? There are special simplicial spheres. What about Bier spheres with 10 vertices? What can we say about that? And here's the answer. This is, in a sense, our experimental result. It says that all Bier spheres with up to 11 vertices are polytopal. So there are no non-polytopal Bier vertices with less or equal with less than 12 vertices. And there is this enumeration. There are 88 non-threshold complexes on 5 vertices and 48 corresponding non-isomorphic Bier spheres, and they are all polytopal. Why I mention here non-threshold complexes? Because by our theorem 1, we know if a complex is a threshold complex, weighted majority game, then it is automatically polytopal. So here the first step was to find all non-threshold simplicial complexes. There are 88 of them, and then to find a way of testing if they are polytopal or not. If they are polytopal or not. By the way, here there are links to 2 PDF files with complete lists of these Bier spheres and polytopal realizations side by side with them. This is just repetition of the Steinitz problem. Okay, so I mentioned theorems 1, 2, and 3. Theorem 1 and 2 are perfect characterizations of weighted majority games and roughly weighted majority games. And theorem 3 is this result about, experimental result about polytopality of Bier spheres. Here, I think I still have a little more than 20 minutes. So I will give you a flavor of the proofs of these 3 theorems. And first of all, theorems 1 and 2. How do we show that, how do we characterize weighted majority games, for example? And in general, how do we handle polytopality? You have how you are given a combinatorial sphere and you ask, is it polytopal? Can you? And proving that it is not polytopal is one of the most challenging problems actually in the field. And you can say that large parts of the theory of oriented matrix, as developed by Bokovsky, Sturmfeld, Richter, Gebert, Ziegler, and others, is developed for several objectives, but one of these objectives was to test non-polytopality. So it is very difficult to check non-polytopality. But if you say, if I prescribe a normal fan in advance, or just a fan, and say, is there a polytopal realization of this simplicity sphere so that the normal fan is the one we prescribed in advance, then it is much, much easier and better understood. And I will simply, first of all, jump to this proposition. So this proposition is, well, I hope you can see the proposition. Please alarm me if you don't see the whole screen. So this is an important result, a very nice and interesting tool, and it appears in many different papers and in 20, 30 years ago and just a couple of years ago in different ways. And so it says the following: if you are given an essential complete simplicial fan and a matrix whose rows are rays of this fan, and you associate real numbers to rays of this fan, and these real numbers are captured by this vector H. And then you say, is it? And then you also given a matrix G, and you ask, is this fan a normal fan of this polytop? So matrix and H is given in advance, and the answer is yes, if and only if the following condition is satisfied. I will not, of course, try to discuss very much this condition, but I will just say what is the meaning of this condition. It says something is a convex polytop if it has a convex support function. And in this case, the only candidate for the support function is really given by the condition 2. And the condition 2 simply says that a convex function, a function is convex if and only if it is locally convex. And local convexity is expressed by these equations 10 and 11. And I will not discuss this anymore, but come back to so-called submodular functions. So we introduced a submodular function, K submodular functions, where K is a simplicial complex, in our first publication about Bier spheres. And I will not again discuss very much the precise meaning of these inequalities. If you look at inequalities 4, 5, and 6, it is some inequalities which involve X is a losing coalition and Y is a complementary set, a winning coalition. So these are some inequalities expressed in terms of the simplistic complex. And the existence of a function of this type, we call such a function K submodular. And it turns out that a Bier sphere is canonically polytopal if and only if it admits a K submodular function. So that's a criterion, a very useful criterion. And this is some discussion about precise meaning of these inequalities, classification of ridges in the Bier sphere in terms of these delta diagrams. There are 3 types of them. And this is another description of inequalities for K submodular function. And strong polytopality is just, so this is just theorem 1. I repeat, just theorem 1. And strong polytopality of threshold complexes is a property which characterizes threshold complexes completely, or weighted majority games. This is a proof, an outline, but I would like to spend more time in the last part of my talk on theorem 3. So you remember, theorem 3 is experimental and algorithmic, and I want to share with you some insight, and maybe some of you might have ideas how to improve and how to extend our boundary of 11 vertices to 12 or more vertices to test polytopality of simplicial spheres. So theorems 1 and 2 provide complete characterizations. And as I already mentioned, if we increase the number of vertices, non-polytopal spheres should emerge. And our theorem says that it does not happen. There are no non-polytopal spheres, Bier spheres, below 12 vertices, up to 11 vertices. So in particular, the Möbius Bier sphere, you remember, I will mention it later again, is polytopal. This is something I discussed in Moscow and Petersburg last fall, and with Taras Panov and Viktor Matveevich and others. So this is a report that Möbius Bier sphere is polytopal. It was a candidate to be maybe the first non-polytopal Bier sphere, but here is a proof that it is polytopal, and I'll explain the methods used in this proof. So here is the algorithm. Okay, you have an explicit simplicial sphere, Bier sphere associated to simplicial complex K. So what do? If K is threshold, it is polytopal. We know it by theorem 1. So what do? We take a simplicial complex K, which is non-polytopal, which is non-threshold, and approximate it as good as possible with a subcomplex which is a threshold complex. So we want to test Bier K, and we construct Bier L, where L is a threshold subcomplex of K. And we want to compare canonical star-shaped realizations of these 2 complexes. On the left is the star-shaped realization of the threshold complex, which is, as we know, polytopal. And the corresponding star-shaped realization of Bier K is obtained by some form of geometric stellar modification. Like you see that you take the polytope on the left and then take a wedge, cut out a wedge, and it is no longer polytopal. But it is not convex anymore. But then you say, maybe I can make it convex by some radial modification. And this is what I'm going to do. I take this non-convexity part and take some point of vision outside, and then try to modify this realization to make it convex. So by so-called radial variation of vertices. Radial variation of vertices. And let me do it with some detail with this special Möbius sphere. So you remember a Möbius sphere has Möbius, well, minimal triangulation of the Möbius band has 5 vertices, and it is Alexander dual just to 5 cycle on the left, 5 cycle on the left. And I want to know, I want to prove that the Bier sphere associated to this Möbius triangulation is polytopal. So what do? We first of all, we take this cycle 1, 2, 3, 4, 5, 1, and it is, as we know, non-threshold, and therefore it is not polytopal. But I will easily make a threshold circumcomplex K1. K1 is threshold. Simply I take L. Let me see if I defined it previously. No, L is just you take this cycle and take. Oh yes, L is written in the last line below. So as you can see, L has just 2 edges, 1, 2, and 2, 3, and of course vertices 4 and 5, and it is polytopal. So you can imagine that geometric realization of L is precisely this complex, this convex polytope on the left. So that's Bier L realization. And then we add edges. Initially we had 1, 2, 3. Now we add 1, 5, and obtain a larger complex K1. Add again 3, 4, we obtain K2. And finally, when we add 4, 5 edge, we obtain a full cycle. So K3 is precisely the full cycle, and we want to prove that Bier of K3 is polytopal. Bier of K3 is polytopal. What do? We apply this strategy. We go step by step by one modification at a time and try to convexify. So our algorithm should automatically convexify. And what do we see here? Here we see theorem 1 produces, of course, an algorithm given a threshold complex. You easily you have a canonical convex realization, and here we if we use this weight distribution, this measure, then it produces this cycle of length 5 with this threshold alpha, and then the corresponding Bier sphere has canonical polytopal realization with 10 vertices in 4-dimensional space. 10 vertices are the rows of this 4 by 10 or 10 by 4 matrix. So this is the first convex polytope we start with. Now we proceed using this convexification strategy, choosing appropriate points. We radially perturb and obtain convex realization for Bier sphere K1. And we continue. Again, one single stellar modification of this sphere, it becomes non-convex, but we again convexify and obtain by new radial modification this convex realization of Bier K2, and finally this algorithm, this program produces convex realization of the Bier K3, where K3 is the Möbius triangulation. At this point, you can if you say how can you be sure, we can say, okay, we have database, go there and use this and use some tests, your favorite test, to show that this is a convex polytope and that the phase poset of this convex polytope is precisely the sphere Bier K3. But here, of course, we we wanted to be sure ourselves that our algorithm works correctly. So we wanted an independent check that this is really a convex realization of the Möbius-Bier sphere. So again, this picture represents Möbius sphere as a combinatorial object. Usually in the language of Bier spheres, you have vertices like 1, 2, 3, 4, 5 here, and corresponding vertices with bars, 1 bar, 2 bar, 3 bar, and so on. And then the top dimensional simplices, 3-dimensional simplices of the Möbius-Bier sphere are listed here. They basically form the fundamental class of this Bier sphere if you take it into account the signs which are written on the right-hand side. So you have the list of all simplices, facets of the combinatorially described of the Bier sphere, and you have what we claim to be polytopal realization, and then we use some standard program like polymake of Yevgeny Gavrilov and Mikhail Yozvik. We take this matrix, and as output we obtain on 10 vertices. Polymake will give you 0, 1, 2 up to 9 as the set of vertices. So the polymake lists all the facets, and all you have to do is to compare and to convince yourself that these two lists, these hypergraphs, are really isomorphic. And it is indeed the case. Actually, it can be proved not by brute force. There are tricks how to do it, but I guess, well, and this can be applied to basically any other Bier sphere from our list. Okay, so this was my in a sense presentation of theorems 1, 2, and 3, with some emphasis on this experimental or algorithmic side. For conclusion, I should say that our enchantment with Bier sphere, the more we study them, the more excited we are. And of course, some of you might say, okay, that's very nice, but why would we be interested in Bier spheres? And just as several sentences commenting on that, I already mentioned that Bier spheres naturally appear in the context of polyhedral products, and they, in some sense, that leads to monomial Bier spheres, which naturally extend the theory of Bier spheres, and monomial Bier spheres are related to monomial ideals and commutative algebra. So one would expect, and I'm pretty sure it will be the case, that Bier spheres will interact with toric topology in many interesting ways. Well, okay, I don't want to advertise it anymore. My time is almost up. Oh, okay, sorry. I have to mention diplo simplex again. If I had time, I would talk about diplo simplices. So you remember diplo simplex is just if you take union of, let's say, regular simplex and the dual simplex and take the convex hull, they appear as Voronoi, as shown by John Conway. They surprisingly they appear as Voronoi polytopes of important lattices. In particular, the picture I showed to you of the cube as a diplo simplex in dimension 3, actually it happens again in dimension 7 and in some other dimensions with particular lattices. Okay, enough of the advertisement. My time is, I maybe have still a few more minutes, but maybe it's a good time to finish. Dear Viktor Matveyevich, happy 80th anniversary, and one of my favorite pictures hopefully for one of our future projects. This is
So let's thank the speaker. Does anyone have questions?
Hello.
Hello.
I'd like to ask a question about the simple games. So the definition seems highly connected to cooperative games. So the cooperative games is when we also have a set of players, and there's any subset of them can form a coalition. And so the game for each coalition we prescribe an amount of earnings they can earn, for example, money. And the question is whether they can distribute money they earn between them fairly. So there will no sub coalitions that will riot, and there were some theorems of Bondrov and Shapley prescribe when this can be possible when some inequalities holds. So this distribution is the set of such distribution is called kernel, and the kernel of a game exists when whenever the set of some inequalities holds. This inequalities seems really similar to the one you mentioned. Submodel about submodular functions. And so I'd like to ask, well, do you know how these simple games and cooperative games are connected, and maybe these inequalities are how they are connected with these inequalities you mentioned?
Yeah, this is an excellent question. This is a very nice question. I from the distance, I would consider simple games and cooperative games the same thing. And you say the problem they solved, Shapley and others, is the problem of fair division of what they earned. In other words, so I think that a connection, well, thank you first of all for this suggestion. I haven't thought about it. And just my first response is, I'm sure a connection exists. And at the same time, it will illuminate one another in some possibly interesting way. And especially with roughly weighted games. So what you are referring to is just weighted majority games, I think, but maybe I'm wrong. So just for now, not to talk too much, I think the connection exists. And also this, as you say, that what we call K submodular functions might be related to what Shapley and others, some inequalities they use. I'm eager to look at it. And so if you send me an email, I will know who you are, so we can continue discussion.
Yes, thank you. I'll definitely send an email.
Yeah, thank you very much.
More questions?
Алло.
Yes.
We'll be happy if we met each other soon, not waiting 10 years, which we met.
Yes, I'm looking forward to that. I'm just saying that it would be nice to celebrate your 90th anniversary or later. But in the meantime, we can celebrate regular birthdays. So I absolutely looking forward to that.
I'm waiting our meeting soon. Best wishes.
Thank you.